today I'll be talking about, you heard about VLF, so I'm going to go to the other side of the electromagnetic spectrum and talk a little bit about millimeter wave, in higher frequency and lower wavelengths than microwave. So first, I'm going to tell you what 5G and millimeter wave is. Then I'm going to talk about on-chip millimeter wave antenna arrays. I'll talk a little bit about reconfiguration and reconfigurable arrays. Then I'll touch upon a little bit on antenna measurement challenges at millimeter wave frequencies. All right, so what is 5G? When I ask this question from people, I get very different answers depending on whom I ask. So if you ask a cell phone carrier, or you ask a scientist or physicist or antenna engineer or microwave engineer, you get different answers. So I decided I ask AI. So there is this OpenAI platform that's available to everyone. It's been recently opened up. So I punch in 5G. You can describe in text what you want, and the artificial intelligence basically spits out a bunch of pictures. So I ask AI, and this is what AI thinks of 5G, which is basically a cumulative knowledge of the database that the AI runs on. So it involves some sort of a wireless communication, cell phones probably, portable devices, and maybe high-speed interaction or interconnection or massive connection between portable devices. I like to use more scientific explanation and definitions for 5G, which is millimeter wave. IEEE defines millimeter wave as wavelengths between 1 to 10 millimeter. That corresponds to 30 to 300 gigahertz. So that's where we can think about 5G, 6G, and beyond. The commercial examples are a little bit different. So if you ask Verizon or T-Mobile, maybe 3.5 gigahertz is considered 5G. So looking a little bit down on the frequency spectrum, we have where most of the 3G, 4G systems currently operate, somewhere around 1 gigahertz, maybe a little bit less, depending on which country you are, or Wi-Fi system, 2.4 gigahertz, 5 gigahertz. And these what we consider conventional microwave systems or bands. And then they go to lower wavelengths on the right side. And recently there are bands that used to be not available to us. For example, 8 to 12 gigahertz, which was exclusively used by DoD for X-band applications. FCC has opened up bands within that area. So that could be considered also 5G, and also higher frequencies or lower wavelengths. One of the things that is amazing and a driving force for this technology is machine-to-machine connection or connectivity. People call it Internet of Things. Different people, again, calls it differently. But here on the y-axis, I'm showing the number of machine-to-machine connections in 2022, which is 12 billion connections. This number excludes all cell phone connections. So what are these? These are your smart thermostat. These are systems in your car. These are your refrigerator, your office connectivity, etc. How many people on planet Earth? Recently, there are 8 billion people on planet Earth, and we have currently 12 billion machine-to-machine connections. So I think, and this is the highest growth area in wireless communication. It's not driven by number of cell phones, etc. It's driven by this IoT. Okay. As far as applications for millimeter wave bands, I think most of us are familiar with it. 3D video, 4K screens, high data rate communications, self-driving cars, etc. Let's take a little bit closer look at millimeter wave bands. Again, IEEE definition of millimeter wave bands is something about 30 gigahertz, 30 to 300 gigahertz. But if we use a little bit looser definition, We have this sub 6 gigahertz bands that's shown on the left, between 3 to 6 gigahertz. Then you have bands that are above 24 gigahertz. Some of these bands have traditionally been used for satellite communication. Nowadays, you do have a band in 257 shown here that is about 27 gigahertz, and another band closer to 40 gigahertz. So 30, let's call it 39 gigahertz. These are what some of the cell phone manufacturers like Apple, Ericsson, Samsung are currently using for next generation 5G communications. All right, major problem with millimeter wave propagation are free space path losses. So here I'm showing free space path loss as a function of frequency. The y-axis is loss in decibels, and the x-axis is frequency. I'm showing few gigahertz to 300 gigahertz. And there are two plots here, one for 1 meters of communication propagation and one for 100 meters. It's clear for us that if you move from 3 gigahertz or traditional microwave band to millimeter wave band, you have massive losses. So this needs to be compensated. How can be compensated? We'll talk about that a little bit. The other issue is, okay, the solution is probably not very high frequency at all the time. So the solution is probably use high bands, mid bands, and low bands for various forms of communication. So you can use traditional microwave band for longer range communication, but maybe inside your building for near range communication, you can have millimeter wave for high data rate, high speed communication. So I'm not advocating that we should be all using millimeter wave for all applications. Specific attenuation is also an issue where you have about 60 gigahertz, you have this massive attenuation due to water vapor and oxygen. And there is a unlicensed band about 60 gigahertz, about 5 gigahertz, 6 gigahertz. US, Japan, and Europe has different definitions for these bands. So approximately 5 gigahertz is available in unlicensed band, about 60 gigahertz. Basically, nobody wants to use this because of this problem that I'm explaining here. It's highly lossy, but it could be used for some near short distance communications. Just to take a look at the summary of losses. Losses means in order to compensate for those, we need to have high gain system, mostly highly directional antennas that I can confine all the fields, all the radiation pattern of antenna in one direction and create narrower beams so I can compensate for these free space path losses. So a typical antenna may have more than 30 decibels of gain. And a normal omnidirectional dipole antenna with 2.1 dB of gain will not work for a millimeter wave. So we need to move into highly directional antennas. Here are some of the comparisons between 2 gigahertz and 28 gigahertz. Looking at the path loss, we're comparing 84 gigahertz at 200 meters to 107. This needs to be compensated somehow by either your electronics or your aperture. Just a quick note on evolution of microwave circuits. In 50s and 60s, we used to use waveguides. Waveguides are still used right now for high power applications. They're beautiful devices. TE and TM mode transmission lines or guided waves. Then we moved to PCB devices and MMICs, and now a lot of these devices are fabricated on a chip, either monolithically fabricated or some sort of a hybrid or heterogeneous assembly or packaging of these devices on the chip. Of course, we don't know what the next generation is, and I'm not trying to predict that for the future. My team works on millimeter wave antenna arrays. So these are passive devices that can provide you with that high gain in mmWave band. So I'm going to take a little bit look at what is currently available in this mmWave band. If we did a survey of literature on 60 gigahertz on-chip antennas, these are antennas that are fabricated on silicon, so you can directly integrate them with high power, basically your TR modules or transmitter receivers or other electronics. So the typical gain of an on-chip antenna is minus 10 to minus 5 dBi. Why? The efficiency of antennas are extremely low. Efficiencies are between 1 to 5%, whereas we like the efficiencies to be 90, 95% and above. So this is a real problem. And I'll talk a little bit about why this efficiency is the problem. In order to create high gain mmWave antenna arrays, this problem needs to be solved. Why are these antenna structures very lossy? Well, it comes down to the substrate that we make. And I showed the evolution of microwave circuits, and we have basically moved into PCBs, printed circuit boards. And these printed circuit boards have also been used for antenna and antenna array structures in the past few decades. In a typical PCB material, you can choose a PCB material with low permittivity, permittivity of 2, 3, 4-ish. In a silicon structure, you cannot do it. Silicon has a permittivity of 11.9. Even if you choose a non-doped or undoped silicon, or a silicon that has high resistivity with a low loss tangent, you still need to deal with this high permittivity. What happens if you put a dipole or a patch or whatever your structure is, if you put it on the silicon, basically, because your permittivity is 12 on one side, 1 on the other side, most of your radiation pattern basically sucked into your substrate. So you're basically radiating in a direction that you don't need. That's why a traditional on-chip antenna has a radiation efficiency of 1%. Only 1% goes in the direction that you want. People have tried to do a lot of tricks, and almost none of them work. For example, you can put a ground plane there, and you can bring up the ground plane, create a thick oxide layer underneath your antenna, or you can create a very bulky, what we call a silicon lens in the back or in the front, to basically create a quasi-optical system that basically directs the radiation pattern. All these systems have low efficiencies, and the efficiencies are shown here. We work on a structure that is suspended in air in order to basically isolate the antenna from a lossy silicon. We use a process to suspend the antenna in air and create a higher efficiency antenna array. In this particular example, the antennas are suspended in air using SU8 posts. SU8 is a photopatternable epoxy. You do a lithography system. We create these we create these posts. These are about 35 micrometers tall, and that 35 micrometer elevation above the substrate is enough to decouple by radiating, let's say, patch antenna from your substrate. This is the how the structure looks like. We basically have some feed structures. With radiating structure is a patch antenna that is suspended on these small posts. This is my patch. We have some mechanical support in the form of SU8, and we feed the structure with a capacitive feeding, so there are no vias in this structure. This is the antenna geometry. This antenna is designed at 60 gigahertz, so because of that, the dimensions are fairly small. A mmWave antenna array on a chip will easily fit on your cell phone. The wavelengths are very small. Although the antennas are electrically large, maybe there are 10 lambda, 20 lambda long, but the wavelengths are very small, and the array can be high gain, but very small, physically very small footprint, electrically still very large. These are some of the detailed structures of the numbers are shown in micrometers. So at 60 gigahertz, the free space wavelengths is 6 millimeter long. Okay, these are some of the impedance bandwidth. This is S11 in decibel. We want to be less than minus 10 dB. And since it's phased arrays, if you have a narrow beam, you need to be able to scan your beam. You don't know where your target is, so you need to continuously scan your beam in different directions. You need to scan your beam in different planes. So here we're showing impedance as you scan, as your radiation pattern changes, the input impedance to the antenna also changes. So we are looking at the impedance at the broad sides, and then when we scan in 55 degrees in E plane and H planes. Patch arrays are not to be great in scanning because of their radiation pattern, but these structures can scan up to 55, sometimes 60 degrees. And the radiation efficiency is fairly high, depending on the scanning. At least the broad side is more than 80%. Taking a little bit more detailed look at scanning. So we look at two cardinal planes, E plane and H plane. A typical patch may have this cosine. You can think about this as a radiation pattern of my unit cell, and then times the antenna array factor becomes this radiation pattern or realized gain. This is a 9x9 antenna array. So it's not a very large antenna array, but perform fairly well up to 50-55 degrees. The fabrication process, how do we make these structures? As mentioned earlier by the first topic, these are done using lithography systems. So they're fabricated inside the clean room. They're on wafer, and we use lithography, etching, deposition techniques for various structures, depending on what materials we have. In this structure, the antenna is fabricated on two wafers. The top wafer has the patch antenna, and the bottom wafer has all the transmission lines, and this what we call a capacitive feeding structure. So there are no vias connecting the top layer to the bottom. So the patch is basically excited using a proximity effect or using a capacitive pin. This is the example of a 4-inch wafer. This is a glass wafer that we have a bunch of 9x9 antenna arrays, and we design different antenna sizes, and maybe the designs are slightly different in each because we don't know what we're doing. So we test all of them, or some variation, we create variations of the same design. How do we measure these structures? We can measure these structures if I can excite all elements, but I don't have active electronics to excite an array of 81 elements. That would be a $1 million project for me. Therefore, I need to be able to do passive antenna measurements here. Here we use RCS. I won't go into detail, but we look at the radar cross-section and backscattering method to measure the antenna gain or estimate the antenna gain. For these systems, if I have chance at the end, I'll talk a little bit more. We use robotic systems. So at even higher frequency, let's say 100 gigahertz. Your wavelength is about 3 millimeter. So if you want to have a good phase error measurements, let's say 1 degree, you need about 1/300th of that, about 10 micrometers of spatial resolution to be able to do this type of measurement. So if you don't care about phase error, you don't need robots, but if you do, you need very precision movement. The antenna beams are also very narrow, so traditional testing of an antenna on a tripod will not work for these structures. Your antennas are very tiny, your beams are tiny, and you need a precision measurement system. So in this system, you have an antenna array here, and then you have another probe, basically, or another or either open-ended waveguide or a horn antenna that helps with testing. This is an example of a antenna pattern measurements, comparison of the simulation and the measurements fairly match, at least at broadside and closer angles to the broadside. And this is the measured radiation efficiency, about 83%. We look at the efficiency versus frequencies. Antenna can operate from 58 to 62. When you scale these antennas to millimeter wave, your absolute value of your bandwidths are massive. Like 3-4 gigahertz of bandwidth versus traditional bandwidth of, let's say, hundreds of megahertz for traditional antenna, or tens of megahertz. Correct. This is the array efficiency. So, and also in this case, the gain is about 23 to 24 dB, which is expected from a 9x9 array of patches. Can you make this on PCB instead of a silicon? Can you avoid using fabricating your antenna in a clean room using lithography system and order this into a PCB shop and fabricate it? Yes, with some delicacy, you can choose the right substrate, and certain vendors can fabricate very fine features on your PCB. The vias are typically a problem here. You need to pay attention and model these vias in your full wave simulation, whether using CSC or HFSS or other tools. So everything that is the result of that fabrication defects needs to be carefully modeled in your structure. For testing purposes, it's quite challenging. We have a connector. So you have a 60 gigahertz antenna that the element spacing is very tight. You have a lambda over 2 element spacing, that's 3 millimeter. So I want to fit a connector inside each unit cell in the back of the PCB so I can test it and I can excite it and test it. So this brings a lot of challenges. The connectors that are at these frequency, and 1 millimeter or 2 millimeter connector, coaxial connector, is very fragile. So it needs to be, these are not something that we can plug in and test right away. It requires careful design. This is some EM simulation of how the scanning works. For example, here we're scanning at 30 degrees. By changing the phase of each element, you can scan these beams in various directions. And that's what the attraction of these phase arrays are. We are electronically scanning our beam. Here you show them, I'm showing them wavefront basically generated here and moving in this direction. That's where the scanning angle is 30 degrees. These are PCB-based antennas. So we, because I don't have the flexibility to fabricate all the features that I want, that's available to me to lithography step, I have a lot of limitations as far as line width, spacing, via sizes, etc. The performance here are not as great, but you can scan up down to 40 degrees in these patch arrays. Here are the simulated patterns for E-plane and H-plane, similar to what I showed earlier for a silicon-based. This is a fabricated device. So the top left figure is basically a patch array. You see vias on each patch that goes to the back of the substrate. This is the back of the substrate. We have substrates that we put these connectors in the back, and there are some that we populate a 9x9, and there are some substrate that we only populate the center element because we use the active approximation. We measure one element and we infer the radiation pattern. Most definitely, you need onboard termination and calibrations for these antenna measurements. Everything here is basically reflecting at these frequencies, all your connectors, everything. So what you do is we typically have these onboard termination calibration, whether it's a short, load, open, whatever it is, you put it right next to the antenna that you need to test. Otherwise, it doesn't work. The measurement results here is a comparison of a simulation and measurements. The 10 dB impedance bandwidth is 3.6 gigahertz, 6%, typical for a patch. A little bit better than a normal patch, but the absolute value of the bandwidth, somewhat irrelevant here, is very large, so you can do whatever you want. Typically, you don't have the electronics that have such a large bandwidth anyways, so you can't really use all that bandwidth, at least not yet. we use a robotic setup to measure the antenna pattern. This is the pattern for a single element. So we excite one element and we measure the radiation pattern for that. And we compare simulation with measurements. These are done at 60 gigahertz. So you do require a high end or end of the line network analyzer. In this case, goes up to 67 gigahertz, and everything can be measured using coaxial cables. Those of you who may have visited my lab yesterday, you may have seen a waveguide-based system that goes up to 110 gigahertz. So that's a W-band system. At those frequencies, you can no longer use coaxes. You need to excite your antennas with waveguides, which creates a lot more complexity. Imagine a moving device that is connected to a waveguide. The instrumentation is pretty complex. Here we're looking at the measured versus simulated realized gain and directivity. Directivity is slightly higher. The difference between the directivity and your realized gain is your efficiency or losses in decibel. Here in this case, 85% was the measured efficiency. So we can also infer the radiation pattern of an antenna with measuring a single pattern. What we do is you multiply that by your array factor, simulated array factor, and you create, you basically can synthetically build your beams. So this is the radiation pattern of the entire 9x9 antenna. Okay, in summary, I just showed you that we can build these systems, preferably on a silicon substrate, so we can integrate them, and we can also create these structures on a PCB structure. I do have a little bit more time, or okay. How much time do I have? Okay. I want to talk a little bit about W-band systems. So W-bands can be used for radar applications. There are shorter wavelengths. There are advantages of using shorter wavelengths for certain applications. We are interested to create systems that are reconfigurable. There was an earlier talk, a little bit touched upon reconfiguration. Reconfiguration basically can be in the form of frequency reconfiguration, polarization reconfiguration, beam steering, etc. So it's a broad, loaded term. There are different ways to reconfigure systems, optical, mechanical, material, electrical, and I'll show a little bit about one of the techniques that is used here for W-band. A typical reconfigurable system, RF reconfigurable system, uses pin diodes or some sort of a varactor. We use semiconductors to create a junction that has some form of capacitance, and manipulating that capacitance by manipulating the reverse voltage or bias of that diode, you can basically manipulate the capacitor, create a reconfigurable system, whether it's a pin diode or a Schottky diode. RF MEMS was the area that in maybe between 2000 to 2015, I would say overpromised, under-delivered. Still a very exciting area. You can create switches that are extremely linear, meaning you can put a lot of power on them and the properties don't change. In semiconductor devices, this is not the case. These are highly non-linear systems. So not only the pin diodes needs some threshold voltage to get things going for the junction to be biased, but also it doesn't work when you have a lot of incident power on it. So these are not attractive for certain, let's say, transmitter applications. Maybe for receiving mode, they're okay. There's been a lot of buzz about liquid crystals. There are a few companies that create phased arrays, using liquid crystal. Kymeta is one of them. The idea is you do beam steering by basically biasing your circuit. Liquid crystal is used in TVs also. Basically, the idea is you put a very large electric potential between two electrodes and you reorient the polarization of your dipoles that are inside your material. So these are called ferroelectrics, and there is a ferromagnetic version, dual version of that, using BST or other materials. Turns out that BST is highly lossy. Liquid crystal is not, but the reconfiguration that you get from these materials are very tiny, and you may need to apply a few hundred volts to basically change the permittivity by a few percent. In practice, not a great idea. Here we showed some kind of like novel reconfiguration system using paraffin. Paraffin is a wax that is has a very low loss tangent. If you look at the materials at 100 gigahertz, it's hard to find a material that has a loss tangent with 10 to the minus 4 in front of it. Loss tangent means losses in my material. It's basically your electromagnetic wave converts to heat due to this imaginary part of the complex permittivity. So we tried to use this material that this is the structure. Basically, you have some sort of a transmission line. You load it with this capacitor and this paraffin there. You put some joule heaters, electric heaters underneath it. You heat it up. Paraffin expands when it becomes liquid. And you have this encapsulated device that has a variable capacitor. This plate goes up and down. So we did create these structures. This is a slot antenna. So you can think about this slot antenna. We have a bend in the slot. The bend is so I can get a, if I don't have a slot, I get a null in my broadside. This is operating at a second resonance frequency. What you see is we have this CPW line that is used to excite the slot. At the two ends of the slot, we put these variable capacitors using paraffin. Remember, the slot is operating at 100 gigahertz. By manipulating the capacitance of the slot, basically, I'm tuning my transmission line. You can think about the slot as a transmission line. So basically, we're electrically tuning the length of my antenna, therefore changing the resonant frequency. This is the radiation pattern. It's bidirectional. You have basically peak radiation pattern or directivity in two directions. These are fabricated on a glass substrate. We built some electrical models, understand how the slot works, how these variable capacitors can interact, which location to put these capacitors, where to feed the slots to get them to maximize the figure of merit here. Figure of merit here is how much change in frequency I can get by applying this variable capacitor. Here's a closer view of these variable capacitors. Basically, you have an encapsulated structure that has this paraffin with these heaters, and you heat it up, and the capacitance changes. So we can make circuit models, and then we can make full wave simulation models to predict these systems. So we start with ADS, and we move to HFSS or CST. Here's a fabricated device. This is a slot. There are two capacitors on the two ends. You see some DC lines here and a joule heater looking at serpentine line. These joule heaters are in, they have one ground, and then there's one DC bias here. And this is a plate that is on top. This plate goes up and down and change basically the length of your transmission line. These at 100 gigahertz, you have to use probes. We use GSG probes, ground signal, ground probes. This is the signal, and then you have two on the other side. We do some displacement measurements. So this is an optical setup that we excite. We basically apply DC voltage, and you basically look at these capacitors moving or displacement, mechanically displacing. That corresponds to, these are basically measurement results. When we apply a few volts, the height of the capacitor works. The advantage here is, unlike MEMS devices, we use 2 volts to 5 volts. So we don't need hundreds of volts. These devices are fabricated on a wafer. This is an example of a GSG probe. So it's a 110 gigahertz probe. As you can see, it's connected to the waveguide. Now at these frequencies, I can no longer use coaxial line. Coaxial won't support a TEM transmission line, which is coax, cannot support these modes. So you use a waveguide, and this makes things very, very complicated for a test setup. Now you have a waveguide that needs to move, etc. We have some DC probes. These are pretty easy. So these measurements are done on a probe station. It's connected to a frequency extenders. You may have seen it in my lab yesterday. And these frequency extender basically extend the PNA from 60 gigahertz to 110 gigahertz. Basically, they're multiplexers or multipliers. So in this case, also the antenna is basically put on a thick foam layer so that the chalk of the system doesn't impact your measurement. Calibration is very tricky at these frequencies. If you calibrate and you move your cables a little bit, everything is messed up. So a simple bend of a coax cable, we induce few degrees of phase error. So you need to consider these when you design your system. So we use a calibration techniques here is called offsetted shorts. So you have shorts with various frequency, various lengths that you use for calibration. This is on a Smith chart. The short looks like a short on the Smith chart, and you change the length. Basically, it moves around the Smith chart, and that's how you do calibration. I showed the antenna measurement system, and this is one of the challenges of mmWave antennas. My group works on some near-field antenna measurement system and some far-field antenna measurement system. I showed this system in the past, and this is an example of how the robotic setup moves. Basically, we have a software that's connected to a PNA, connected to the robot. We can precisely move the antenna in the direction that we need, and then we measure the radiation pattern of the antenna. This is done on a coaxial. This is a 60 gigahertz measurement. You may have seen the waveguide version of that yesterday. The setup is quite complicated. We have frequency extenders, cables, coax cables, etc. So the system is quite complicated, but it's required for these type of on-wafer, on-chip antenna. So even if you're clever enough to design the antenna, if you're clever enough to test, to fabricate the antenna, you still need to do a lot of work to do an antenna gain pattern measurements. So that's maybe the message that I want to give. This is a picture of the setup that we currently have at Georgia Tech. It's a 67 gigahertz 4-port network analyzer that's connected to some frequency extenders. These are from Virginia Diode. Use waveguides or open-end waveguides or horn antennas for testings, and we have a group of 5 undergraduates who basically writing scripts using MATLAB, etc., to program the robots and read and write from the network analyzer and do some of these gain measurements. Thank you again for your attention.
Let's thank the speaker. Time for one question. Please wait for the mic.
You mentioned the challenge in selecting a substrate that silicon has.
You mentioned the challenge of selecting a substrate material because silicon, which is cheap and convenient, has a problem with absorbing the RF that you want to go out into the world. How much success have you had with alternative materials? I know you mentioned glass. I know sapphire is a material that you can use as a chip, a wafer substrate. But you seem very focused on silicon. So it sounds like there's a reason to pick silicon despite the electrical challenges that it poses.
Correct. Thanks for the question. The attractive about silicon is the direct integration of your active electronics, mixers, power amplifiers, LNAs, all the passive components that are fabricated already on the silicon that needs to be integrated with a larger antenna. So integration or monolithic integration is the main driving force. There are different integration techniques. Glass is also an attractive substrate, has a permittivity of 3.8. It's a lot better than silicon, not as low as we like for typical antenna structures, but glass is an attractive substrate. Other semiconductors like gallium arsenide, etc., have very high permittivity also. They're very challenging. Sapphire is a great material. It's great for making transmission lines if you don't want radiation, but the permittivity is still very high, about 9. So we also use sapphire for some of our applications, but permittivity is very high and substrates are very expensive to be used. So I think glass, short answer, glass maybe it's a good substrate to take a look at.
Okay, one more very
Yeah, I'm sorry. I just had a quick question. I missed the part where you had talked about the lambda on the on chip. So what was the target lambda between the poles on the substrate?
You mean the spacing between the
Yeah, the
elements?
spacing.
We
You said
typically
3?
3 millimeter, correct.
And in a super heterodyne receiver, what does that give you for diversity gain at 60 gigahertz or whatever the target?
Can you repeat the question?
So I guess. the land target and diversity gain, right, on the C path. So what's the expectation with 3 nanometers of lambda? Are you still going to see a diversity gain and in the receiver?
We haven't looked into that, so I don't know the exact answer to your question, but about lambda over 2 is what we typically design these structures. The reason for that is we don't want to get grading lobes at higher angles,
I
and
just think about it as a scattering environment, especially in those times.
right. So we do look at the port-to-port coupling between these elements, and they're fairly small, minus 25 dB, minus 30 dB. You basically get no port-to-port coupling after you move 2 elements from each from each. We look at the cross-pole performance, but just to note, most electronics cannot support this spacing right now. So 3 millimeter is too small to fit all the radio system inside it. So although we work on these passive devices, we do not work on the active components that goes behind these. That will be a different field. Correct.
Okay,
Thank
let's
you.
thank the speaker one last time. Thank you.
Thanks, Chip.